In this video, we're going to take a look at what are called metathesis reactions, or more commonly known as double displacement reactions. In these reactions, we're going to take two ionic compounds, and I'm going to just note them as AX plus BY. So we have A and B as your cations, X and Y as your anions, and in the course of this reaction, they will switch their partners if a reaction is going to happen. So we're going to end up with AY and BX, where we will have switched the partners of each ion. So A used to be with X, now it's with Y. B used to be with Y, now it's with X. One thing to note, of course, we should still end up with cation-anion pairs. We're not going to see cation-cation pairs or anion-anion pairs, right? So in order for this reaction to happen, for this to occur, we have to have something happening in the products. We need at least one product to be an insoluble solid, which is called a precipitation reaction. That's one. Water, that can be another product, which is a liquid, or a gas. And that's called a gas evolution reaction. We're going to see otherwise, if we don't produce a solid, water, or gas, nothing happens. So we're not going to see the reaction actually take place then. So this part in purple here is our driving force for the reaction, the reason for it to occur. And this is something that you'll talk about in Gen Chem 2 when you talk about equilibrium. When you produce a solid, water, or gas, you are removing things from your equation. And when you get things out of the way, you make more room for more products to be made. And that's kind of the easy explanation for it. So as you do that, you make more room for more products. The reactions happen very quickly. You've seen this before, in fact, in your everyday life. You know, growing up, you probably did that baking soda and vinegar thing, where you produce all those bubbles. That's producing a gas. Or maybe in previous chemistry courses, you've seen precipitation reactions, where you're producing a solid, where the solution gets cloudy. That's the driving force behind these. In order to do this, though, we have to consider, we're going to break this down. We're going to first look at precipitation reactions, and then we're going to look at the water or gas producing reactions, and that'll be another video. So let's look at precipitations. First thing I want to do is recall that in solution we abbreviate SOL''N, just to be brief. In solution, ionic compounds as abbreviated CPD, if they're soluble, are strong electrolytes. So remember that something like CaCl2 is not really CaCl2 in solution. It's really calcium ions and chloride ions. And in fact, we have two of the chloride ions, right? But the point is we have the ions present. And what we're looking for in a precipitation is we want to look at our solubility rules and identify if we mix two sets of ions, are we going to form something that will be a precipitate? Is it going to form a solid, something insoluble? So for some example, if we have sodium sulfate, again, which is really sodium ions and sulfate ions, if we were to mix a solution of calcium chloride and one of sodium sulfate, we would have these four ions present. And what we want to do is evaluate each pair of cation and anion, and evaluate if one of those pairs is insoluble or not. So let's look at calcium first. If calcium is bound with chlorine, that should be soluble, right? We know chlorides are soluble. Calcium is not an exception. so that's good. If calcium binds with sulfate, that is something that is insoluble. So we'll remember that. Let's just double check the rest of it, because sometimes you'll have two precipitates. Sodium ions, when they're with chlorine, should be soluble. I'll give you a hint. Remember, anything with sodium will always be soluble, but let's just double check for fun. And sodium with sulfate should also be soluble. So the sodium and chlorine will always kind of be present as our ions there. But the calcium and sulfate, once they find each other, they will rapidly create a solid, an insoluble compound. So we might actually write this equation like the following. We've got our calcium chloride and our sodium sulfate, both of which are aqueous. This will always be the case. Your reactants should be aqueous for these reactions. We're going to end up producing calcium sulfate, which is a solid, we indicate with the S there. Insoluble means solid, which unfortunately is the same letter as soluble, but S means solid. So insoluble things, I'll indicate that here in blue, will be the following. That's the combination of the calcium and the sulfate there. And then we also will make technically aqueous sodium chloride. We can write it like that. So we've switched our partners. We indeed found that there was a solid formed in this reaction. The calcium sulfate is formed because once those two ions find each other, they are very happy to come together and form a solid. They have very strong interactions. One thing to note with these, very commonly, is don't worry about those pesky subscripts that we see for charge balancing. We do not take Na2 as an ion. Always we look at the individual ions that are present in this solution. We don't care how many. That's for balancing. If we were to balance this equation, that's when we worry about how many ions. But when we're figuring out the products, we just want to look at all the ions in solution and identify if any pairs will form solids for precipitation reactions. And indeed, we see that calcium sulfate should be solid. Both of those have the same charge, so we're not going to need any subscripts. Sodium and chlorine also have the same charge. We're not going to need any subscripts. So don't worry about those. Ignore these pesky subscripts. Those are for charge balancing only. Ignore them until you're ready to balance the equation. Once you're ready to balance, yes, then you pay attention to those 2's there. But you do not say Na2Cl2. That is the big no-no. Never say something like that. Ionic compounds always come as the smallest ratio of ion pairs. So we're not going to do that. In fact, once you balance this, you'll end up with a 2 in front of sodium chloride. And that's all. So everything else is fine as is. So precipitation reactions. Let's kind of go over the procedure, and then we'll do one more example. For precipitations, the first thing we want to do is determine which ions are present in the initial solutions. Second thing, we want to check the solubility of each ion pair. I'll say even cation, anion pair. So positive, negative. There will be no positive, positive, negative, negative things here. Electrostatics prohibits it. If at least one pair is insoluble, then we have a precipitation reaction. So that's kind of the step-by-step procedure here for determining the products of your reaction, as well as if the reaction is going to happen. We're going to see sometimes if we take some compounds, put them together, nothing happens. And that's all right. You know, it's science, right? Sometimes nothing happens. So let's do another one. Let's say we have AgNO3 and how about calcium bromide this time? Will this react? We have to find out. The ions present in each compound will do in blue here. So that's the first step. We need to determine what ions are present. So in silver nitrate, remember your reactant should always be aqueous. It'd be pretty silly to throw a solid in, although that's not, never mind. We won't go there. We'll leave that alone. So the silver nitrate is made of silver ions and nitrate ions. The calcium bromide is made of calcium ions and bromide ions. We want to evaluate each pair. So let's just go left to right. So silver with nitrate should be soluble because any nitrate is soluble. Silver with bromine, I don't remember. Let's go back up to our rules. All the way up here. So none of the first category is present for silver and bromine together. Rule 2 tells us about bromine. So X minus is present, should be soluble. Oh, but look, indeed we have an exception here. So we will see that silver bromide should be insoluble. So AgBr would be a solid. And let's just check the other pair. Will calcium and nitrate form something insoluble? No, nothing can ever form an insoluble compound with nitrate. Nitrate will always be soluble. So the products for this then will be calcium nitrate. Remember that we're charge balancing properly. Calcium has a 2+ charge, nitrate -1. We need 2 nitrates to balance it out. That should still be aqueous because it's got a nitrate on it. It's soluble. Aqueous and soluble are the same thing for us. And then we have the silver bromide solid. It does not matter the order you put these in. You could put silver bromide first and then calcium nitrate second. Doesn't matter. So essentially we're left with our precipitate, our silver bromide, which will form little solid particles that will filter out of solution. We're then left with a solution of calcium ions and nitrate ions, and we represent that as calcium nitrate, even though in reality they are still calcium ion over here, nitrate ions over here, whatever, they're all over the place. But they don't actually form like a compound necessarily. They're still floating around in solution. All right, so that's precipitation reactions. In our next video, we'll evaluate reactions that produce water or gases, which will be called neutralization reactions.